We have talked about many things about signal systems, and now we go back to our original scope, which we basically talk about the transform. So now we will talk about S. Now, so we showed Laplace transform and Fourier transform. In Fourier transform, we are using J omega. In Laplace transform, we are using S. But they have a very, very similar property. So if you see Laplace transform, they were given by xs, which is minus infinity to infinite, xt e minus st dt. That's how things looks like. In case of Fourier transform, they were given by xt e minus j omega t dt. Is it right? As you can see on the screen. So if you compare this Laplace transform and Fourier transform, they are quite similar. The only difference is, as I said over here, they just switch j omega to s. So j omega to s, j omega to s. Both of them, they try to transform from time to frequency, reverse form from frequency to time. So they are very, very, very similar, except few exceptions. S. So I once, in the beginning of the lecture, I once explained that Laplace transform covers all the complex plane. In Fourier transform, they only covers a part of the complex plane. So Laplace transform has more domain compared to Fourier transform. That's one major difference. That's what I can say here. Laplace is a more generalized transform. So they can have more generalized transform. Fourier is a subset. It's a part of Laplace transform and many similarities. So, once again, Laplace transform is a more general term. It covers all of the complex plane compared to Fourier transform, which confined to a unit circle. So, why we are learning Fourier transform first? Because it's simpler, of course simpler, and then they have a lot of similarities. So let's see how things are different. In S, this S is complex value. So this S, you can divide them to real value and complex value. It has a purely imaginary value. So it has purely real value and purely imaginary value because it's a complex value. So let's define them as delta like this. When this is 0, then this is equivalent to Fourier transform. So say that this is 0, the real part is 0, then this is equivalent to Fourier transform. Right? So that's the reason that Fourier transform is called as subset of Laplace transform. Laplace transform can represent Fourier transform. Fourier transform cannot represent Laplace transform because this is a higher, more coverage. So let's just do some math to prove this. So we define, how do you call this? How do you call this? Sigma? No? Pi? No? stop joking and let's move on. So we have this relationship. This is our Laplace transform. This is our relationship in this S, which is complex value having purely real and purely imaginary part. Let's put them over here. Let's divide them like this. So minus infinity infinite xt exponential minus this one and minus j omega t dt. Is it right? Just switch it. And if you compare these two, you can see that this and this, if you define a new variable, say yt, equivalent to that, they're actually the same. Right? So what you can say here is this Laplace transform can be viewed as Fourier transform of xt times e. What's the name of that? Pi? I forgot the name. Sigma? What? So is it? Sigma? Okay. So sigma t. If I make a mistake, that's your fault. So we can view Laplace transform as xt multiplied by e sigma minus sigma t, multiplication of this one. This one function, Fourier transform of this one function. That's what we can view like that. However, if you remember Fourier transform, we briefly introduced convergence issues. Convergence issue is we basically talk about that, okay, when they not go to certain value but typically going up or diverge, then we cannot have Fourier transform. So we introduce several conditions. However, this one directly influenced by those convergence issues because of this. So let's think about E minus sigma t. So sigma is a real value, so we can consider as a constant value. And how we can draw this? If you draw them in t, that is E minus delta t. Let's bring one example that if sigma is positive, what happens? Sigma is positive, say E minus 2t, then they looks like this. If sigma is negative, E minus 2t, then they all looks like this. So this E minus sigma t, depending on the polarity, positive, negative of those sigma, they can diverge. So once again, remember, Laplace transform can be viewed as a general form of Fourier transform of this whole function. But there is a multiplication of E minus sigma t is given here. So this one may diverge, may converge. So depending on polarity of this sigma, they may diverge. So we have to define what is this sigma is. So let's bring on another example. Say that we try to have, this is our cosine omega t, for example. Say this is our cosine omega t. In time domain, our cosine omega t is given by like this. Right? And then, when they diverge, when they converge, like this, I think I mentioned this one at the first chapter. If you have sine, if you try to draw this is E minus delta t when delta is positive. If you want to draw xt times E minus delta t, they will look like something like this, and they converge to certain value as possible. If E minus delta t, delta is negative, then the multiplication of ET, E minus delta t, they will oscillate between them but they diverge. So we cannot have a certain value. So this value, especially the polarity of this one, directly influence the convergence and divergence of the signal. This is what you can see in here. So let's think about that. So, once again, the polarity of this one, delta, directly influence if you have converge or diverge. They decide it. So we introduce a new concept only exists in Laplace transform called the reason of convergence. So reason is like area, the area that the signal is convergent. That's what you talk about. So ROC, we call ROC. So in Laplace transform, we introduce new concept, say, reason of convergence, ROC. So in Laplace transform, you have a result, say, okay, our Laplace transform is given by something like this, comma, reason of convergence is what? They're always given like this form. So once again, we have a result of Laplace transform and comma and reason of convergence. That this value can exist only this reason. That's the kind of pair we will continue to see in Laplace transform. All right, so once again, let's have an example. So if you are asked to find a Laplace transform of, say, what is it? E minus AT ut. Let's try to find Laplace transform of this. Let's try to find Laplace transform of this. In Fourier transform, if we do the Fourier transform, they were given by it looks like this in Fourier transform. In Laplace transform, they are given like this. As you see before, if you plot that, this one, so so let's leave this one for a minute. Let's leave this one for a minute and try to solve this. When you are asked to solve, so we have already learned Fourier transform. So when you try to ask, okay, let's try to solve Fourier transform. Then how we start? There is ut over here. So okay, they become not zero, higher than zero. So we move that, and we calculate. All right, these two we multiply them together. They will be given by a plus j omega t dt from 0 to infinite. And then, okay, let's have a plus j omega minus over e minus a plus j omega t from 0 to infinite. Say, okay, in this case, when you put infinite, this one becomes 0, and when you put 0, this one becomes 1. The result will be minus a plus j omega over 1 times infinite. This one becomes 0, minus, when you put 0, this one becomes 1. So that's your answer. That's your typically what you have done by far. Right? No? Someone smiles to me, someone says, I don't know, someone says, So this is a typical process when you do the Laplace transform, straight transform. So, but really? That's how you do in continuous time Fourier transform. But really, is it true? Is it really true? Because let's look at this part from here to here. From here to here. You have assumption that if you put infinite, can you see this hiding over here? If you put infinite over here, if you put infinite over here, yeah.
The lights here, because it's reflecting, you cannot see what is written.
In here? Okay, so let me rewrite. So let's rewrite this one again later. So let's rewrite this one more time. So by far from here you can see that, right? So let's do it one more time. So when you do that, it will look like e minus at times e minus j omega t dt. If you multiply them together, they were given by minus a plus j omega t dt. Right? And then when you do the integration of this, they were given by minus a plus j omega over 1 e minus a plus j omega t. That's integration. Right? And then you are putting infinite to infinite for 0. And then this one becomes, say, a plus j omega over 1. If you put infinite, this one becomes 0, right? E minus infinite, so this one becomes 0. Minus, if you put 0, this one becomes 0, this one becomes 1. So this is our Laplace Fourier transform. That's why we have them by far, right? But really, is it true? From here to here, when you put infinite, we assume that they become 0. But this is assuming that this value over here is positive. So e minus at, if a is positive, then when you put infinite to t, then they become 0. If a is negative, if a happens to be a big negative value, what happens? Say this one minus this is minus become positive, right? So what happens over here is e a lot of infinite value. So they become infinite, which the value cannot exist. That's why we talk about convergence issue right now. So we just ignore those convergence issue by far, but which has directly influence over here in this case. So this example shows what happens if you have convergence issue. This one tells you that some values, if you go back to our table, this one says A has some reason, some range. If A is larger than 0, then that's fine. A is lower than 0, you cannot have the value. So regional convergence is already we considered in previous cases. So E minus AT may decay, which is we can have the value, may explode, diverge, which we cannot have the value. There's a problem. So let's try to have those examples. Let's try to introduce those examples in Laplace transform case. This is example 9.1 in our textbook. So let's try to solve this. So Laplace transform, okay, there are this from infinite to infinite. What is our x? Our x is e minus at ut, which is exactly what we did previously. This is exactly what we did previously. We have minus at ut beforehand. And this is our value, our x, minus st dt. This is our Laplace transform. In Laplace transform, we have assumption that they can be divided by delta and j omega t. It's possible. So let's divide them. Let's do that. So from minus infinity to infinity, e minus at times this one, which is e minus delta j omega t. And let's relieve ut dt, but in case of ut, we can ignore that. They become 1 from 0 to infinite. Right? Ut is what? Unit function. They are 1 after 0. So from minus infinity to 0, there's nothing over there, so we don't have to care about. That's the reason we can divide them 0 to infinity. And let's do some mathematics over here. Like this. So from here, we will see that this is this. Good. All right. So this is equivalent to that. We have this to be our Fourier transform. So if you remember the previous case, this is equivalent to the case that let's go back to this case. So minus infinity to infinite, e minus a plus delta t ut e minus j omega t dt in our previous example. Say, in our previous example, we have e minus at ut. If a is positive, they converge. Okay. A is negative, they diverge, which is not okay. Right? In the previous example. We say E minus AT UT is our transform in Fourier transform. If AT is positive, they converge, which is okay. If A is negative, the minus AT become positive, so they diverge. So this is not okay. We cannot have a value. Likewise, when you see, if you compare these two, this is case for this. If you compare these two, my A delta is equivalent to A over here, is it right? If you have a question, please ask. If you have a question, please ask. No? Okay, then I'll go. Now, what you can see from this analysis here is if A plus delta is larger than positive, then it's okay. If A plus delta is smaller than negative, then it's not okay. So now we define that this is our region of convergence. This is our region of convergence. The region, not REASAON, region, the area, the range or space that we have converge, we can surely converge. That's called region of convergence. So in this region, then they do not converge. So they will be excluded from region of convergence. This region is the area that we surely have convergence, right? So this one is called region of convergence. So can I erase this? Can I erase this? Bottom one, the red one. So if you want to draw this, if you want to make a picture, how we can do that? So let me rewrite this one. So you can do the Fourier transform as a result of Fourier transform, comma. The region of convergence is A plus delta is positive. That's what we will write. Of course, not like this, not this form. We try to make this one more general form. More general form. Is it any bad reason? Is there any obstacle? If we just write them as, okay, A plus S is larger than 0. Once again, from here, S is delta plus J omega. Let's draw this on a space. So on a space in complex domain, this is real, this is imaginary. All right? And any arbitrary point at this domain is delta in real and omega in imaginary. Right? So what this one says over here is actually this delta is larger than A. That's what they minus A is what they say. So when you see that, that means this delta over here is larger than certain value. Let's say minus A is over here. This fixed constant, right? A is constant. So their value is, their real value is larger, for example, than this certain value. They can be point here, they can be point here, they cannot be point here. This is not possible. So you can draw a line like this. Say that any value over here, they have delta larger than minus A. Is it right? So this graphically, this is our regional convergence. Graphically, say, all right, our delta is larger than minus A. That's this. And there's no obstacle that we just extend it. Say real part of S, which is delta over here, is larger than minus A. It's the same one, right? Graphically like this, and we just say original conversion is real part of S larger than minus A. That's what we can say. So that's it. That's what we have seen by far. Question by far. Wow, it's already 20. So what we see over here is two things. First of all, Fourier transform and Laplace transform are quite similar, except Fourier transform, Laplace transform can be represented by real time and complex imaginary part. Real part and imaginary part. Because of it, we may have diverging issue. This may converge to certain value, it may diverge to infinite. So, to avoid that, we introduce a new concept called region of convergence. We have the result of transform, comma, that this result of transform can exist. We give a reason that this result can exist. That's how it goes at regional convergence. To calculate, we do those mathematics and calculate the reason and then make it original form, which is graphically given by like this. They are larger than certain value. Interestingly speaking, those regions of convergence always happens by vertical line. It does not come like this because, remember this, if you remember the first part of this whole class, if you have E minus st, for example, they will have E minus delta t times E minus j omega t. If you want to make plus, doesn't matter. This one, in complex domain, this one is in charge of oscillation motion in time. This part is in charge of maximum value that this oscillation motion can reach. So, this oscillation motion does not have much contribution to convergence or divergence. They just oscillate. But this yellow, which defines the envelope, the maximum amplitude that they are oscillating, decide either they converge or they diverge. So those regional convergence are really related with the real part of this complex value. So they're usually depending on this sigma. Because of it, we will have, say, they will be larger or smaller than the real value. That's the reason we usually draw line vertically, not laterally. So if you see the regional convergence graphically, they always draw line in vertically. The reason is only the real part contribute the decision of convergence and divergence. That's the reason. Okay, question. Okay. So let's erase this. In previous example, we have solved e minus at ut, and the reason of convergence is larger than minus a. That's what we see in previous case. Let's change this one to e minus at still hold, but let's use minus t. So this is case that we want to have e minus at u minus t. So here and here are different. Let's see how things are different. So let's put minus over here. And then how things will be different. Now, u minus t is what? U minus t is what? They are not 0, smaller than 0. Right? So now, instead of this, we have minus infinity to 0. That's the only difference. Right? And then, how do we do it? So this one becomes minus infinity to 0, meaning that t value over here is negative. T value over here is negative, right? T value over here is negative. So, negative, which is positive. Right? So, now, if A is positive, what happens? The value over here is positive. What happens? If they are positive, which is previously convergence reason. In this case, in previous case, as this is negative, this was positive, right? So minus t was negative. Minus times positive, so minus t was positive. I'm sorry, negative in previous case. So if this value is positive, negative, positive, which is whole negative, which they converge. Now situation changes because t become negative instead of positive. So minus negative is positive. So minus t is now positive. If you multiply positive by positive, they diverge. So now we want to have negative a delta, which is a plus delta should be smaller than certain value, meaning that delta is smaller than minus a. So if you want to do that, the reason of convergence, assuming that this minus a is same value, which is over here, it should be smaller than those a, minus a. So they will be like this. Can you see the difference? We change a kind of direction of those unit function. So in previous case, which is shown as white over here, they are from 0 to infinite, which is positive t. Because of the positive t, this minus t become negative, right? Because they are negative, we want positive a plus delta. To get a positive a plus delta, then real value of s, which is delta, should be larger than minus a. That's the reason of convergence in this case. Current case, which is shown as yellow over here, you put minus t. That's the only difference. if you put minus t, then it was from 0 to, instead of 0 to infinite, they become 0 to minus infinite, reverse way. Because of it, the value of t is negative. So minus t become positive. So if you have a plus delta negative, then they converge. So to get a plus delta negative, we want to have regional convergence smaller than those a. So those white, we want to have our regional convergence larger than minus a. By simply switching this, we want to have smaller than this a. But what about our transformed value? What is our transformed value? Let's calculate what is our Fourier transform. So from here, if you do the calculation, you will figure out that where do you start? Let's this one for a minute. So let's try to have for the white case, previous case, which is given by integration of 0 to infinite. I'm talking about the previous case, the white case, e minus a plus delta t e j omega t e minus j omega t dt. If you do the integration of this, there will be minus a plus delta plus j omega over 1 exponential minus a plus delta t times e minus j omega t from 0 to infinite. 0 to infinite. Is it? There's an integration of exponential. Is it right? Then, well, you can see it. If you put infinite, then because of regional convergence, we assume that a plus delta is positive in white case, which is e a minus at ut case. Then this is positive minus infinite becomes 0. So this one become 0 minus, when you put 0, there will be 0, there will be 1, there will be 0 in total, E0, similar to our previous example, and the result is A plus delta plus J omega over, and by minus, will be cancelled by minus over 1, which is, this is what? This is S. So S over A is the result. Question. I see 3 of you has a question mark on your head, so please ask. I think you already know my style. If you just wait, I'll just move forward. So I'm just waiting. but please ask.
E 마이너스 j 오메가 t 쪽은 0에서 무한대까지를 어떻게 처리하는지.
이쪽이요? 저기요? So when this one is infinite, as I said, this one is in charge of oscillation. Right? However, this one, which is in the regional convergence, they go to 0. So even though they have some value, multiply by 0, they become 0. That's the reason. If you put 0, then this one becomes 0. This one total 1 becomes 1. It's still 1. So the result is, this is our Laplace transform, and our region of convergence is real part s is larger than minus a. This is our answer. So you have to make sure that you have to do that, because if you don't do that, you cannot move to the next part. Let's try to have the second example, which is this. So the yellow case, so we have minus t over here. Now 0 to minus infinite. So we will have 0 to minus infinite instead. This is still the same. So they will be still the same, like this, minus infinite. And their regional convergence is what? So that's the only difference, and you can calculate, I think. The only change what you see here is the regional convergence, which is now they become real part is smaller than minus a. That's what you see over here. So that's the two cases we have comparison. So what we see in here is the result is not quite different. Only difference probably comes from the fact that this one is real part larger than minus a. This part is real part smaller than minus a. For the simplest case, we can see on the example. And next one, we talk about several different combinations. So before we move on, question. So by far we talk about ut minus ut, but still they have same minus at over like that. Now we have more than one reason of convergence. So keep in mind on this. Can I? Please show some reaction so I can follow. All right, so let's have one more example. Three e minus 2t ut minus 2e minus t ut. This is example number 3. When you see this one, as we already learned about this, if ut is positive, just ut instead u minus t, then we already know what is regional convergence. So before we move to calculate the Laplace transform, let's see if we can find where is our regional convergence first, intuitively. So this one, 3 times e minus 2t ut. So their regional convergence, based on this analysis, A is 2 in this case, right? A is 2. 수진 학생 알겠어요? 아니, 모른다고 물어보는 거 아니에요. 그냥 아무나 찍었어요, 보이길래. So, once again, E minus AT UT case, we have regional convergence larger than minus A. So from this intuition, A is 2 over here. So we intuitively say minus A, which is minus 2, they are larger than minus 2. That's what is regional convergence in the first part. In second part, their regional convergence is what? Now minus A is minus 1. So the regional convergence is like this. So this one and that one in same function has different region of convergence. If you combine them together, the first one, they are larger than minus 2. The second one, they are larger than minus 1. So in this case, what is our regional convergence? They are overlapping. So regional convergence is what? In this region, we guarantee that the value converge, meaning that the value exists. So in this region over here, none of these converge, which is definitely not region of convergence. This yellow region over here, the region over here, this one converge, this one converge. So we can guarantee that this and this, both of them converge, which whole function converge. So we can guarantee that. What about between them? We can guarantee that the first one converges, but second one does not converge, which we cannot guarantee that the whole function converge. So the regional convergence of two different regions is overlapping area, the common area of both of it. So in this case, the regional convergence will be this region over here. Okay? So regional convergence now is intuitively say, okay, they are larger than minus 1. That's you can see over here. And what was the result of this? What was the result of this? The result was as this in this example. Right? So following this, we can notify that this one, the first one, say 3 times like this, 3 times s plus 2 over 1 is the Fourier transform, Laplace transform. This one, 2 is constant, s plus 1 over 1 is their Laplace transform. That's it. Result. And what you have to write here is this is your Fourier Laplace transform, comma, this is regional convergence. Of course, as you can see in the slide, you may combine them together like this. Of course, you can say, okay, let's combine them over 3 times s plus 1 minus 2 times s plus 2 equals s squared 3s 2 over s plus s minus 1. You can, either one is fine. Either one is fine. Doesn't matter. In here, you're probably familiar with one thing. I see you take a homework of the control theorem in the beginning of the lecture. So you may familiar, I think all of you are familiar with pole and zero. Pole and zero. If you have, you're probably familiar with something like this. What is pole? And zero. Pole is the value of s or j omega make numerator 0. That's a pole. So in this case, pole is, and this one becomes 0, which is s equals minus 2 or s equals minus 1. That's the pole. 0 is s or j omega making numerator 0. So in this case, 0 will be s equals 1. 0 typically show as a circle. Pole typically show as x. So let's go back to here. Let me redraw this. So regional convergence in this case is larger than minus 1. That is our regional convergence. If we want to plot pole and 0 in this diagram, then pole, which is minus 2, and minus 1 is over here. 0, which is 1, is over here. So you have regional convergence, you have 0 inside the regional convergence, pole at the boundary or outside of regional convergence. There are several reasons we are doing this.